Good afternoon, everyone. I'd like to welcome to this afternoon's panel session. I hope everyone's enjoying the conference and enjoying a very good mixture of panels, technical presentations, and a lot of good advanced technology. What we'd like to try to do with this panel session itself is really address the implementation, utilization, and coordination of advanced energy concepts within the government and Department of Defense. Just to let you know, too, we've had a few slight changes in some of the speakers here for the actual panel itself, too. But I think what you'll find out is that we have a number of good representatives here from not only from the government, from the civil side, NASA, from DOE, and also from the DOD sector here, right, too. And we have a couple industry representatives here too that have worked either with large or small companies here too, and they're going to give us their perspectives on some of the trying to get advanced technology into some of the government programs, some of the pros and cons that you'll see with that. So I hope everybody enjoys themselves. Just to introduce myself, my name is Mike Pizar. I'm at the NASA Glenn Research Center. I'm chief of the photovoltaic and electrochemical systems branch out there. So I've been working advanced power technology in PV and batteries for my entire career there too, and have had the chance to work with and know a lot of the people up here on the panel. So I think you're going to get some very unique perspectives here as to what we have in terms of advanced technology, how some of the advanced technology that is out there right now starts to really get incorporated into the mainstream sector. And also, just to emphasize itself too, there is a lot of coordination between the different government and DOD programs. So with that, why don't we get started? First speaker is going to be Evan Jones from Pacific Northwest National Laboratory there too. So, okay, Evan.
Thank you, everybody. I don't have any prepared briefs ahead of time, so I was just going to have a conversation here. And just happy to entertain questions if you have any while I'm talking, and obviously we'll have time afterwards as well. So first I was going to touch a little bit on base with what we do at Pacific Northwest National Laboratory in terms of power and energy systems. I think really our primary areas are we're very strong in lithium batteries, lithium battery chemistry primarily, and also we do a lot of work in solid oxide fuel cell power systems, and we've also done work with starting generator. So those are really the big things that we work on. And we have a lot of programs with DOE with the battery chemistry and the battery systems. With those programs, DOE is an organization that emphasizes collaboration across industry, universities, and the national lab system that they have. There's about 13 DOE national laboratories. There's an expectation that they work together on projects. Most of the large proposals submitted by DOE have an expectation of some very large partnering. And one example is on a lithium battery, a battery chemistry initiative. And it involves 3 national laboratories, 4 or 5 universities, and several companies. And that's very common for a DOE initiative of large scale like that, where they will have multiple parties involved. Another example that doesn't involve power and energy, but does involve electricity, is one that was set up by DOE where we are the prime. And it is a demonstration of smart grid technology and using bidirectional control systems called transactive control to communicate between the individual devices up to the transmission system. And that involves 11 different utilities and 5 different infrastructure companies, private companies, to set up the IT system for that. That's another example of the kinds of large-scale multi-partner things that happen within the DOE system. We also do a lot of work across the military organizations as well. So we work a lot with, for example, in the solid oxide fuel cell system, we work very closely with NAVSEA and the Navy on building the solid oxide fuel power systems to be demonstrated on UUVs. So in that case, we work with Boeing because they were the prime contractor, and then we provide the power system. And then that was demonstrated for NAVSEA with a small pool trial. So those are, and then we also do work with, for example, with TARDEC, materials joining technologies. So many times when we work with the military, it is typically 2 to 3 entities involved in those organizations. We would not normally have 6 or 8 different parties involved when we began working with the military organizations. I think as we look ahead, what we see is A lot of times what we see when we're working with DOE is there's a really nice transition, because DOE really does a lot of fundamental science and technology. And anytime you're dealing with these hard engineering problems that we typically are dealing with, there's always an element of critical science that has to be solved. So a lot of times what I've noticed in my career, I have seen the Department of Energy develop some basic technologies that then get transitioned and leveraged by the military. Solid oxide fuel cells is a great example. Solid oxide fuel cells were developed for many years by DOE, and then are becoming demonstrated now within the military defense system. So that's an example. A lot of technologies then transition that way. The batteries are the same way. There's a lot of really great research that happens at the military laboratories, and there's a lot of great research that happens at DOE, and that can get leveraged as they move into large-scale production and demonstration of battery systems. So those are some of the examples from an energy perspective that we do a lot of. We really don't do a lot of work in photovoltaics, any of the science behind that. We do a lot of work for DOE in terms of energy technologies, building energy efficiency, LED lighting, and things like that. So we don't do much work in power conditioning systems either. We don't really do any work in power electronics and power conditioning, not at our laboratory. Our primary emphasis is on batteries, battery chemistry. We're very strong there, and we're very strong in solid oxide fuel cells, and we've done some very nice demonstrations with starting generators. So those are the primary technology areas. I think also when you look at DOE's client set, mission space is very different than a mission space for a military organization. So DOE's mission space is to really transform and improve and benefit the U.S. people and the U.S. economy. So they have this gigantic overarching mission. They also have a very big spread of TRL levels. So they go from a very basic level of fundamental science, where they are encouraged not to really pursue a practical application. It's meant to be fundamental science for its own sake. And a lot of times those really great ideas in there turn out later to have some very strong practical application. But DOE has some very fundamental science, and then it has some very applied programs where you will do a TR level 7 or 8. And you have all of that mixture of capabilities and staff within a single organization, such as at PandE and the other national labs as well. And I'm sure you'll hear from the rest of the organizations here a very similar story of organizations that span across all of those technology levels and then reach out all the time to work together. I think as I have worked in the energy space, I've noticed that that capability set or competency helps people to reach across different organizations. Because every organization, like the Army and the Navy and the Air Force, their missions are very different. They are to arm and equip, train, and fight wars. And as a part of that, they will need things like advanced storage systems or advanced power systems. But the group of people that do that support those missions underneath the main primary mission set. But for the technical staff to work together, they need to reach across their peers, their technical network. And so I think what happens, at least what I've seen in the government, is that you form these technical networks that span across all of the different agencies and groups, because they have a common interest with ultimately supporting a particular mission. So that's something that I have found very effective and I think works really well if you can use your technical network, span across different agencies and organizations, universities, government, private industry, and then with that then you can really solve some hard problems. So that's really all I was going to say. Thank you.
Great, thank you. Thank you, Evan, for starting us off so well with that, too. Up next, too, we're going to transition over to the space side a little bit. Randy Furness will be up next, too, and Randy is the division chief for the power division here, too, and just gone through a reorganization and trying to incorporate not only some of the advanced research technology into the engineering aspects, too, but I'll let him really just give a brief update here. I believe he has some charts here on the what we do here, particularly at NASA Glenn here, in terms of the power, cover the range of all that stuff. So,
great.
Randy?
Thank you, Mike. Would it be okay if I step down here so I can see the charts? Can you still hear me if I do that? Okay, good. I would like to talk a little bit about what we do in power at NASA Glenn. Mike just mentioned that we've recently reorganized how we do things. That's an important thing to know. We've, for decades, we've had our research people in a separate organization from our engineers doing systems engineering, development engineering. Is it working? Ah, thank you. We recently reorganized to put all of those people together so that we have the people working from basic TRL 1, 2, 3 research all the way up through flight hardware development and operation. In one organization, the Research and Engineering Directorate, which is then divided up by core competencies. So we have a power division within that directorate, and that power division contains all aspects of power related to space and aeronautics. So that flavors what, I believe that flavors what you'll see. Now we'll see if I can get, there it goes. So I will show you, this is the taxonomy as it looks from NASA Glenn. I mean, you all have your own in your heads taxonomy of power systems. To us, when we think of sources of power, loads that use power, and ways to store energy, they really come into these categories for us. On sources, we have solar arrays, photovoltaics. That's, in fact, that's Mike's expertise, who's here running this session. We also, at NASA Glenn, concern ourselves with the Brayton cycle, still from a solar standpoint, that's largely solar dynamic. There's been a lot of development in the past. There's not a lot going on right now, but it's solar dynamic energy. We have a lot of work going on Stirling, and Stirling is really a heat source. We use radioisotope. We're looking at fission reactors driving Stirling, power generators, and then fuel cells. We all have different ranges of fuel cells for power. Storage, the classic batteries. You can even use, of course, fuel cells. But we also have developed work on flywheels, and flywheels for space application. There's a lot of opportunity there. I mean, you can get into extreme environments where batteries and fuel cells aren't going to be real practical, like the surface of Venus, where it's 600 degrees. Flywheels will work, and I'll tell you a little bit about that. Ultimately, electric propulsion is a big user of power for us. The electric engines were largely developed at NASA Glenn in the 1950s originally, and are now seeing a lot of use in space flight. Communications, instrumentation for spacecraft largely, and then actuators for spacecraft and aircraft. All basically built around the management and distribution of power, and those are some of the key things that we concern ourselves with. This is really looking at a little bit different view and showing the power systems architecture and engineering in the upper left. We show space station because at NASA Glenn we basically designed and did the early development of the power system on space station. In the early years, that was the work packages were split out to different centers. It was later all pulled into Johnson Space Center, but a lot of the simulator work and a lot of the actual hardware development took place in Cleveland. And when there are, to this day, issues, they will still come back to us because the people who did a lot of the original work are here. I mentioned Stirlings. I mentioned photovoltaics. There's some redundancy here, so I don't want to go back through them again. But it gives you an idea of how power development is laid out at Glenn. Again, another look, the same thing. It gives you a little more detail into the regen fuel cells, supercapacitors. We do very little with that, but we do have some on energy storage. Another cut at how we look at including integrated testing of power systems. So the engineering for power systems for us, it does include aircraft, and the big push right now is moving toward a hybrid, potentially all-electric, hybrid electric aircraft. And that's very high-powered components that we're beginning to push into. Solar electric propulsion is another very timely issue. If the asteroid retrieval mission comes to pass, that's going to be all based on solar electric propulsion. And the propulsion module will be run out of Cleveland for that. There's some other examples here of things that we have worked. The bottom line of this chart is to just point out that it's not just component development that we concern ourselves with. We do end-to-end power system design from a power quality standpoint, from fault control, from intelligent systems. It's all, we concern ourselves with the whole aspect of power systems. Another look at some of the details around space station, some of the hardware that was originally developed here in Cleveland that all have been critically important to the operation of that system. We do analysis of systems also from a standpoint of laying out systems, original system conceptual design. We have a facility called Compass that will lay out entire mission designs from start to finish and take into account all the systems from power to propulsion to communications. All the people will be in the room developing and designing preliminarily the systems that would support a predicted mission. We will then use the space code. We have this code that was developed in Cleveland. We still use it. It's all around photovoltaics. It has to do with shadowing of components. It has to do with pointing to be able to predict the power that would come from your photovoltaic system throughout the life of the mission and plan for maximum operation. Photovoltaics, there's a lot of history in photovoltaics in Cleveland. This is a good example of working from basic research, from cell design, all the way up through system level development and testing. We do a lot of array testing and cell testing on aircraft. We've tested cells on balloons. And basically run the whole range of system level development around photovoltaics. I won't go through each of these because there's a lot of material in them, but fuel cells, as we mentioned, this is a lot of work we do on fuel cells in Cleveland around testing, around development, stack development. You can see we've been involved with alkaline fuel cells, PEM fuel cells, solid oxide fuel cells, and regen fuel cells because there are different applications for each type fuel cell. Small scale to large scale. We run the whole gamut and have worked this through a lot of the early NASA programs until today. Long history of batteries, lithium-ion batteries. You can go way back into NiCad batteries, the whole development history. The batteries on space station, we've got a lot of the background in. And really looking at batteries for all NASA missions, long duration missions, and systems again, integrating the batteries to photovoltaics, to ASRG, to whatever the sources are. Thermal energy conversion is what we call, basically, this is our work, the work that we do around nuclear. Radioisotope, power supplies, and in particular, the radioisotope power supply for Stirling engine. We've been developing the advanced Stirling radioisotope generator, continuing to do research around that Stirling generator concept in the hundreds of kilowatts looking into, or hundreds of watts looking into up to a kilowatt. And the kilowatt is what we're working right now based on a small fission reactor. And that would be, the initial testing is for surface-based power, not Earth surface primarily, but planetary surface. So flywheels. There has been a lot of history on flywheels. There continues to be some work being done on flywheels. We've taken that technology a long way. through the use of the synchronous reluctance bearingless motor. The bearingless is the levitated rotor. And it has been very successful. It is now a fairly well-developed technology looking for a mission. I mean, NASA sees the value, but it has, at the moment, is not a defined mission. So the work is there. It's somewhat awaiting its next customer at this point. There's some background information on the actual motor design and analysis that led into the flywheel work. I don't need to go through all that for the interest of time, but it's in your package. We also have, related to power, of course, EMI testing is not itself power, but it's a critical aspect of design and development of power systems. So we have this capability here at the center to do our own EMI testing of components and systems. On the PMAD side, again, full range from development through system operation. A lot of current work on power supplies for electric propulsion. Currently the PPU work supporting electric propulsion. And you're all familiar with PMAD. We're always looking for breakthrough areas, but at the moment that is development work. There's more detail that I will not go through, but you have it should you want to review it. And then just mentioning power controls. Ultimately, this is also getting into intelligent controls. It's the concern is with space, you don't always have the ability to respond quickly from the ground, from your controllers if there's a 15-minute lag. So you've got to have the systems that can sense what's happening, react to it on their own. And for the purposes of safety and for the purposes of efficiency and effectiveness. And I believe that covered the whole range. So that's an overview of what we are doing in support of NASA, but working very closely as well with other federal agencies. We do work with DOE. We work with largely with AFRL, the Air Force Research Laboratory, but we work with the other services as well in their research laboratories. And a lot of work with universities through our SBIR program, universities and small companies. So that pretty much covers what we do, and I'm happy to answer any questions if you have them, or we can wait till later.
Okay, thank you, Randy. Appreciate that. I think what we'll try to do is hold some of these questions to the end when everybody has a chance to work with that too. Okay, with that said, we're going to try to change the flavor a little bit and have Rao Chakravarty from Microlink Devices actually come up and give a little bit of his perspective on that stuff. Randy mentioned the SBIR program here too. Rao has a small company with the SBIR program that we've worked with, and he's worked very extensively, not only with some of the NASA stuff, but the Navy as well too. And I think he brings, he's going to talk a little bit about his technology, but primarily how that has infused into some of the DOD and government programs and everything. And I think he's going to share some of his experiences with us with that then. So, okay, Rao?
Thank you, Mike. Maybe I'll also jump down over there. It's easy to see the screen. Sorry, my name is Rao Chakravarty, and I'm the technical director at Microlink Devices. During the past several years, we have benefited a lot from government funding in developing our cell technologies. And what I'd like to introduce you today is, the work that we do on high efficiency, lightweight solar cells and how we are implementing them for different programs. So I'll just give you a couple of examples and tell you a bit of the technology from baseline. I probably have way too many slides. I'll try to skip some of them there. Okay, the top one, that's it. So initially, just me give you a small spiel on microlink devices. So microlink is located in Chicago. We are about 40 employees, and primarily we work on compound and semiconductor device materials. We do foundry services for electronic devices. So our main technology base is epitaxial growth, fabrication, and assembly, and of solar cells. And one of the technologies that we have been very effective in exploiting and developing is epitaxial liftoff technology, which is basically funded mostly by DOE and other DoD organizations like NASA and AFRL. This is basically a technology where you can remove the epitaxial stack that is grown from the substrate and transfer it into another substitute substrate so that you can have a lightweight solar cell and then get some cost reduction by reusing the substrate. So this is the basic premises on which the technology is based. So microlink, basically, as I said, we have got 3 divisions. We have the PV technology one, which is basically related to semiconductor devices with solar cells as the main. We also have RF semiconductor materials growth and some engineering services. So as I said, we are vertically integrated. So we do everything in-house, right from the growth, fabrication, assembly, and test. Just to give you an idea that the lightweight solar cells, what are the different applications that they can be used. And here we have in the middle showing a large area solar cell. This is a multi-junction solar cell based on gallium arsenide technology. And different applications, they can be used for UAV and space applications. They can be used in mobile solar applications, and they can be used in CPV applications. CPV is concentrated photovoltaics. So the reason why very high efficiency cells are very important is I try to give you a small cartoon diagram over here where we try to plot the areal mass density. What is the power that you can get per unit mass as a function of efficiency? And in general, you will find that very low efficiency cells tend to have very high areal mass density. And as you want to operate with high specific power, you like to have very high efficiency and low areal mass density. And in this, you can see that the red dot we have where the microlink devices has developed the triple junction cell, where we have achieved efficiencies in excess of 30%. And at the same time, by removing the substrate, you can obtain very low areal mass density. On the next graph, I've shown here, as I said, that we can remove the epitaxial stack and then transfer it to and substitute substrate. As a result of that, the weight of the substrate is removed from the cell, which is basically the major part of the solar cell weight. So as you remove that, the overall areal mass density goes down. But at the same time, I can take the substrate which has been removed, reuse it several times. And as we reuse the substrate, we can gain a lot of cost reduction. And that is one of the factors that I've shown here, that a typical gallium arsenide substrate, if we reuse large number of times, as I say, here I plotted up to 15 reuses, you can see that the cost of the substrate asymptotically approaches that of the actual reuse cost. So the lower cost is a very important attribute of this technology. So here, cartoon, we depicted how can you do the liftoff process. Once you have the solar cell process epitaxially grown, and then following that, you apply a back metal on top of it, and then it goes through a process where you use chemicals to etch a release layer. Once the release layer is released, the substrate is then separated from the cell, and this solar cell can be is moved on to the back metal. So the substrate at the same time can be reused in the fashion, so it can be repolished and reused. So here, one of the a typical structure I'm showing a triple junction cell, which is a inverted metamorphic cell for the high efficiency development. Here, you can see that the typical growth structure and the various layers that are involved in growing this. This structure has basically about 32 different epitaxial layers, and all these layers are grown in one shot. You use a chemical vapor deposition technique called MOCVD, and then all these layers are grown in one reactor run. On the right of it, I'm showing an external quantum efficiency of this triple junction cell, and the triple junction cell is basically consists of 3 cells. An indium gallium phosphide top cell, and a gallium arsenide middle cell, and an indium gallium arsenide bottom cell. And all these 3 materials are chosen such that they are addressing different parts of the solar spectrum so that you get the highest efficiency possible. You can divide this solar spectrum into more number of small regions, and if you can actually have a material which is respond to each of these small sections, then you can completely utilize the whole spectrum in generating the power. Most of the devices that we have fabricated, we do measure in-house, but also we use NASA Glenn Center's technology and their expertise in verifying the results. And here is one of the cells where we have measured at NASA Glenn, and you can see the efficiency of this particular cell is 31.3%. Is more information about the cell technology. You can show this is on the left-hand side an electroluminescence display which shows that the cell, when it is driven in the forward bias, can glow in the red region. This is the top cell wavelength, and it can tell you if you have any defects. And one you can see from this picture that it's pretty uniformly glowing, and it's a very high quality material. As I told you that these cells are flexible, here to demonstrate that we have put the cell on a 1-inch radius drum, and you can operate that. So you can say that cells can be bent, and it can be stored away in a very small volume. So they are very effective to be able to carry very high efficient, very high power loads into the space. So during this different programs that we have been funded by the NASA, we have developed technologies how to make these cells space qualified. We have not yet completely reached that, but there are several stages yet. So one of those things that we have demonstrated is the technology of interconnecting the cells to make large panels so that these are all space qualified. And also we have developed process how do you kick these cells, apply glass on top of the cell such that they can be radiation tolerant. And at the same time, we have also included bypass diodes into the cell such that when the cells are made into panels, one non-functioning cell is not going to kill the whole panel. We have also optimized the quality of the cell for the radiation that the cells may experience when they are exposed into the space environment, and they have been optimized such that large radiation, electron radiation, when it falls on them, then the quality of the cell is not deteriorated over a long period of time. So once we develop these cells, I'll give you a case studies of 2 or 3 how we are using them. And one of those things that is a very interesting application for the lightweight, high efficiency cells is to be able to improve or increase the endurance of a Raven. A Raven is an unmanned aerial vehicle that is very popularly used in the DoD. Here, by applying the solar cells on the top wings of the Raven, you can actually increase the range of the Raven, almost double the duration. This increases in the flight critical time that you don't have to take the plane back because there is not enough power. Here, the way that we have done it by taking the earlier shown high efficiency cells, you interconnect them and to make into a panel. Because the cells are very, very lightweight, you can put them on top of a UAV and at the same time not alter its performance. So this is here a typical layout that's shown where we included power conditioning modules embedded into the wing panels in the middle section, and the solar cells are laid out on both the left and the right wing. In this particular case, total power generated by the solar cells are about 40 watts, and each cell could generate anywhere between 0.5 to 0.6 watts. And the total added weight for this, because of this, about 111 grams onto the aircraft. So this is a test flights that we have been done with the Air Force AFRL group. You can see here there's a 62% improvement has been observed from a conventional Raven by including solar cells onto the wings. So this is a substantial improvement. It will cut down the cost of trying to acquire more Ravens, at the same time improve the critical mission time. And another area that we have done applied this is in the area of mobile solar power. In the DoD applications, in the mobile solar, the soldier has a very important function of carrying batteries in order to do the communication purposes when he's out in the field. And one of those things a lightweight, flexible panel can do is that he can carry this and do trickle charging of the battery as the day progresses and be able to extend the life of the battery for a longer period. Here are some examples which we have shown. We have done extensive work with the Naval Research Laboratory in developing this technology and in applying that in the field and doing field testing. And here you can see different examples and where the panels can be ganged together to be able to get large amount of power. On the top side, you can see 2 panels. One is an existing technology which is based upon a SIGS, another PV technology, which is non-gallium arsenide. And you can see on top of it, you put the gallium arsenide sheet, which is almost like 1/3 in size. So you can show that the power that you can generate out of these gallium arsenide panels are much larger compared to the existing state-of-the-art technology. So at the same time, we are doing more work in generating power for the soldier on the move. This is another example where a 12-watt portable sheet has been made, and this can be used to charge batteries. And this is very, very lightweight. It's only about 1/4 pound weight, and this can generate 12 watts. And currently we are producing, based on the same technology, 40-watt portable sheets for rapid equipment force at the Army. And these are being currently manufactured and tested initially by the Naval Research Lab and then by the soldiers in the field. So these are just a few examples how the technology that we have developed under some of the government programs are being used by the government in the DoD. So finally, I'd like to acknowledge different funding agencies which have helped us in achieving these results. Thank you.
Thank you, Rob. Appreciate that. So that gave us a little bit of a industry perspective and quick synopsis of some of the technology that Microlink has been working on too. We're going to go now back to the DoD representative for this illustrious panel. And Phil Jenkins from the Naval Research Lab is going to talk about some of the Navy's interest in advanced energy concept technology. Phil.
Good afternoon. My name is Phil Jenkins. I'm from the Naval Research Laboratory in Washington, D.C., on the shores of the Potomac River inside the district. And we are a research laboratory not only for the Navy, but anybody who is interested in our technology, which often includes other branches of the service or even some civilian uses. We've had a long history in photovoltaics and space photovoltaics. And in the last few years, when the DoD became much more interested in renewable energy, we started working with the Marine Corps and now the Army and the Air Force on PV applications for the DoD. So the big problem, the big picture problem, is the logistic trail for supplying forces with energy. That by transporting oil for power or vehicles, we put forces at risk, and it's expensive both to get the oil there and in terms of asset costs as well. So renewable energy, particularly PV, looks very attractive. So here's some numbers to put with this the cost of providing fuels to the front in wartime. If you have just a simple convoy with security, you're looking at up to $12 a gallon for fuel, and increasing that security, whether it's air security or air delivery, the cost can be as high as almost $33 a gallon. So when you think about how renewable energy has to compete with traditional sources, it's a much easier equation if you're competing with $30 oil than $3 oil. So it looks very attractive very early in that process. The real challenges for the military, though, are that the renewable energies as they've been developed aren't really suitable for a military application. And that being, if you think of your typical utility scale installation, it's a panel that is put up, concrete footers, sits there for 20 years generating power. In a military application, they have to be mobile. The transport is limited by, usually ships at best or airplanes at worst, where you have severe weight restrictions, you have volume constrictions, and these systems are set up and taken down multiple times by essentially, cross-trained personnel, right? That they don't have just PV specialist engineers to go out there, and they don't have the same sort of opportunities for construction, whether it's digging a footer for a concrete post or large transmission lines. So I'm going to talk about just a few of the systems that our group is involved with. on this. ONR is developing, the Office of Naval Research is developing a 3 kilowatt electrical generator system to replace the standard TQG, or tactical quiet generator, used in the military today, which is just a diesel generator. And their goal is a 40% savings. And I'll just mention sort of the long-term goal is to only use liquid fuels for transportation, and that all other energy needs are satisfied by renewables. So in this case, they're developing 2 systems. One uses a solid oxide fuel cell burning a logistic fuel, such as JPA, which is typically used in the military, and augmented with solar panels. And the other system is a solar Stirling system, where a burner is used to augment the solar if, at night or when solar resource isn't as strong. And it all fits on a light tactical trailer, which is sort of a standard trailer used to tow small companies around. Okay, also, we were also working on these PV programs with Microlink to develop a small portable PV system for the dismounted warfighter. Over the years, warfighters have had more and more energy demands placed upon them. They now have GPS, and they'll have oftentimes 2 or 3 radios, night vision goggles, and their iPod too as well. So in order to reduce the load, carrying load for the warfighter, we are developing renewable energy in the form of lightweight, high-efficiency PV so that they can go on extended missions without being overburdened by batteries. And the program we've been working on has been evolving over several years. You can see up in the corner of that slide much what Microlink presented. They're the cell manufacturer. And we've come increasingly developing the ruggedization of the panel, and we're about to field the ref panel that I spoke about earlier, 40-watt panel with individual warfighters. All right, there's the ref panel. Okay, also another application, so we've had the 3 kilowatt trailer, the portable PV for the warfighter, and again, as Rao mentioned, the UAVs. So our thrust has been, on the PV side, is to lighten the load and reduce the costs of these high-efficiency cells. That's sort of one of the advantages of going after these lightweight, flexible cells, high-efficiency cells, is that they meet all our requirements in that they're going to have lower mass and they'll have better storage and sort of inherently more rugged. And we have goals of greater than 20% conversion efficiency, less than $50 a watt that's at this high efficiency level, and greater than 1 watt per gram specific power. Right, so one of the directions we're pursuing is what we call fast epi. And these high efficiency gallium arsenide-based cells are grown in chemical vapor deposition reactors. And these reactors are sort of the bottleneck in production, because it takes literally an hour to grow these cells. And if you can grow that cell in a minute or a minute and a half, then you can increase the throughput and lower the cost. So we're looking on ways to increase that epitaxial growth speed. Another way is to look at extremely thin silicon cells. Silicon, of course, the dominant technology in utility scale PV. So right there you have sort of economies of scale in the production. But silicon is inherently less absorbent of light than these high-efficiency cells. So there are techniques of what we call light trapping that allow the light to enter the cell and then sort of bounce around until it's absorbed. So in this way, you have much thinner silicon. Thinner silicon is flexible, and it'll be cheaper in principle. All right, so I guess that's completes my slides. So the Navy is very much interested in renewable energy, and DoD sees it as both a strategical and tactical goal to incorporate as much renewable energy as the system will permit. Thank you.
Thank you, Phil. Thank you for addressing that too. We're going to wrap up the last of the comments with our panel session here with Ted Stern. Ted has been with the industry here for a very long time working renewable energy.
Trying to say I'm old.
You said it, I didn't. But anyway, Ted has a few comments here too. I think we'll kind of wrap it up with that. I have a few comments, and then we'll have a chance too for questions and answers and comments by the different panel members. So,
Thank you, Mike. I'm really going to mix it up here by introducing some of the challenges of technology transition within the government and within DoD and into the commercial market. I'm not really going to talk about Alliance Space Systems. If you want to find out about Alliance Space Systems, you can look at our website. I'm not going to talk about the research that I've done in the last 30 years on photovoltaics for space and for related applications. You can find a lot of my papers in what was known as the IECEC, which is now part of this conference. If you're interested in some of the technology that I've developed, I've worked with microlink devices. I've worked with NASA Glenn a lot. I've worked with the AFRL. I have not worked with your laboratory, unfortunately, but I would look forward to doing that. You know, really what we've seen in the last 5 years or so is a lot of disruptions in the market, in the space market, in the DoD R&D market, and these disruptions have several causes, which I am going to just introduce, and hopefully that'll provide some fodder for some active discussion here. Top button, the big green button? Okay. So, you know, there's some threats to technology transition. We do develop technology in this country at an amazing rate. But in the last several years, R&D funding has been more and more difficult to come by. As I have worked for small businesses in the last 20-some years, I've been the beneficiary of the Small Business Innovation Research, the SBIR program. Developed a lot of technology on the SBIR program, and it is nationally one of the best ways to develop and implement new technology. But SBIR funding has been going down, and also has, in many government agencies, been redirected and reprogrammed to meet other needs that don't make it as flexible and as blue sky or far-seeing as the SBIR program used to be. So this is a challenge that small businesses are facing right now. As that R&D market dries up a little bit, in concert with that, the non-SBIR, or the non-small business R&D funding environment has all but disappeared in this country in the last 5 to 10 years. So a lot of larger businesses really are focused on the return on investment with a relatively short return on investment horizon. However, especially with advanced technologies, advanced energy technologies, if there is not a good return on investment, the long development timelines would tend to discourage them from investing in basic research and the beginnings of applied research. Another disruption to the market has been the what I call foreign investment, or the CFIUS effect. This has been especially prevalent in the area of advanced solar cells, as Han Energy and some other Chinese companies and other foreign companies have been taking the good research that has been done in this country, buying it up in the form of entire companies, and then generally making it unavailable, because we do restrict the technology that we use in the DoD and in the government in general to technology we can buy from American companies. So in terms of the R&D to go and take that good technology and bring it to the specialized requirements of the DoD and NASA, this makes it very difficult. And I'll talk in a second about maybe how do we address that challenge. And that relates to designing to environments. I mean, the reason that the foreign investment inhibits the application to DoD and NASA and other government applications is that they do have specialized environments, and in general, these companies are being bought for their commercial potential, which doesn't address these environments. The other aspect of foreign investment is as these foreign companies invest, and we've seen this in the solar cell market in particular, they will then take a very low-cost technology such as silicon, dump it on the market, and that discourages other technologies from being transitioned into the low-cost commercial arena. So in space, where mostly I've been working in the last few years, 30 years, there is also that implementation cycle. So, a company like Microlink or, a predecessor companies that have tried to take new solar cell technologies into space, such as US Solar with amorphous silicon, find that they have to make a continued investment of resources, even while getting R&D resources from the government. They have to invest their best people and their best technology for a payoff that requires a TRL level increase, spacecraft qualification, initial flight testing, flight experiments, and it can be 10 years easily between the time that you get to an applied development and prove that you have a high efficiency, thin, flexible solar cell, and the time you actually get your first space mission of any size that you can go and produce the flight hardware for. So these are all some of the technology transition challenges that as a small company or even a large company, we face on a day-to-day basis. Now, one thing that we can do to help transition technology better is start, from the perspective of the system acquirer, the acquisition agency, or the prime, to start with the top level requirements, and instead of saying, oh, well, we need more efficient solar cells, or we need thinner solar cells, or, these are problems that are at the very component level. Start with the top level requirements, and then take those requirements and create system level solutions rather than mandating solutions at the component level. And this allows the marketplace to more efficiently develop solutions that address system level requirements rather than focusing on detailed technical operating objectives that are often the driver of specific R&D funding programs. And I don't know what to do about sustaining funding environments. I don't have a good answer to that. Every year, it seems, we face the same problem that Congress can't agree on a budget, R&D programs are delayed. The SBIR programs out of NASA used to come out every year at the same time, like clockwork, and small companies like mine used to plan their SBIR campaigns and plan their funding profiles and their resources to that mechanism, that clockwork mechanism. And now with funding uncertainties, that span has increased. Things move around by 3 to 6 months. Contracting becomes more persnickety in how they deal with the small businesses and the contracting efforts. All this has a disruptive effect on our ability to take technology, develop technology, and transition it to the marketplace. So I would strongly encourage, and a lot of this happens already, to for the funding sources to employ their expertise, both internal expertise that they have available to them, and also external expertise from industry and the CETA contractors, to make sure that the technologies that are being developed are the ones that are going to provide the best payoff, because the R&D dollar is so rare. We need somehow for our ground technology, and even for our space technology, to figure out a way to allow us to continue to use the technology that we've bought that has now been co-opted, and also to be able to export this technology in an appropriate way while maintaining our national security concerns. So not having the European market open to spacecraft technology has definitely been a detractor for the R&D and for the commercial spacecraft market here in the US. And not being able to use foreign technology directly in US systems has been a detractor. So there are ways around it. Maybe we need better ways to handle the ITAR restrictions, the Buy American restrictions, all the restrictions that we in industry have to live with on a day-to-day basis. And for space, we just need a faster way to prove that something is space ready. And that relates back to another disruption in the market that was driven by Elon Musk and SpaceX, and now is kind of filtered out. Now Google wants to go and do something build 1,600 satellites. That's been released in the press, and they want to do it at a fraction of the cost. So there is an impetus to go and make space a commodity market, not the specialized market that we were used to working in that required that level of resources. But we can take that and use that to our advantage by using that commodity low-cost small sats. And now any university with $50,000 to spend can go get into the CubeSat business and go create, program, and get ready for launch of a CubeSat. So that's something that was unthinkable only 10 years ago. So now we have the ability to go and launch things quickly and inexpensively. We need to use that ability to get quick flight test beds so that we can test this technology and get Rouse technology and other technologies into the marketplace and into space sooner. Thank you.
Great, thanks, Ted. Appreciate it. I want to thank all our panelists here. They've done a very good job. We've addressed a lot of areas in terms of specific technology itself, too, programmatics, some of the issues that Ted brought up too about the issues of how do you implement that technology into that, how widespread it is, and everything else too. One thing we haven't really addressed as much too, I thought maybe we can get it into our question and answer period too, but also too, one thing I wanted to take an opportunity to bring to everyone's attention. The government organizations that are represented up here and a number of others too are part of this agency called the Advanced Interagency Power Group. So in terms of advanced energy power development, there is a government organization. Its founding members were NASA, the Department of Army, Navy, the Air Force, and DOE. NIST is now involved with that, as long as a few other government agencies here too. And the purpose of that is really to coordinate and try to collaborate with the different agencies that are funding advanced power technology together, such that not every agency is going off on their own. Some of the government agencies may not realize this agency exists. I'm sure a lot of the public does not too, but I just wanted to use this opportunity to plug the IEPG and just let everyone else know is that what you're hearing that with different mission requirements, different types of programs and everything else, don't think for 1 second that those programs are not coordinated. There are different requirements for the different agencies, and the system is not already perfect, but there are government programs in place that try to coordinate that stuff and try to maximize the use of the limited research funding that we've heard out here quite a bit too. So there is a lot of coordination involved with that. So that is one agency that's out there. There are a number of others in different types of areas as well too. So I just want to make that up too. And the way the IEPG works is that there is a steering committee with representatives from each of the participating government agencies that try to coordinate things, but a lot of the work is done through different, what they call working groups. There is a renewable energy working group, there is an electrochemical working group and everything else too, and those groups in there too, they have regular meetings to talk about coordinating some of the technology that's out there. It's a lot about information dissemination. So if you find out that one department or one research lab from the Army is working on something similar with the Navy that they did not know about, to try to promote that coordination and everything else, to avoid duplication and really talk about things like that. So there are mechanisms in place that allow us to actually take and coordinate a lot of these programs. Now I think what you've seen here today or two is that you've heard a breadth from the different agencies in terms of the technology stuff. agreed it's been a little focused a little bit more on the photovoltaics area and everything, but that's just one example. The same thing is happening here, and we could use the very same examples for battery technology, fuel cells, power management and distribution. It goes throughout and everything. So with that said, I'd like to allow the audience now to participate here too. If anybody has any questions and everything else, would like to hear them. I'd appreciate it if people would step up to the mic, since we are online here too, and this is being recorded for posterity's sake too, so that everybody can hear the questions. So please feel free, and also invite members of the panel themselves too. If we have questions for the other members here too, that would be great then. Okay, go ahead.
Yes, I have a question that perhaps may not be appropriate for this session, but I'll go ahead and ask it anyway. The gentleman from Microlink Devices, whose name I don't remember and probably couldn't pronounce correctly anyway.
Rav Tatavarthi.
Yeah, thank you, Rob. Okay. What is your outlook for the use of gallium arsenide and other advanced solar cell designs for ground-based ordinary application on homes, commercial buildings, and so on?
Yeah, it's a very tough question. We being in the gallium arsenide technology, one of the main hurdles to get into the mainstream business is cost. Currently, gallium arsenide technology is very expensive. Having said that, the silicon technology, which is very cheap, has got the huge advantage being able to be being produced in several gigawatts, whereas the gallium arsenide technology is only being produced in few hundred kilowatt. I don't even think so. So there is a volume that unless there is a real application where you can produce large volumes of these cells, the cost is still going to be very, very high. And the future for the applications on the consumer side is not very bright currently.
If anybody else, any questions, please come up here too. Let me follow up with that too. And I think Rao brings up a very good point in terms of the volume stuff. I think you will find that for a lot of the space or the DoD applications too, the volumes are not quite there and everything. And the one thing we've noticed that there's a lot of very good technology there. It's very high priced right now, but a lot of that, and it's a very difficult concept for technologists and engineers to understand versus economics majors, that it's a business plan and it's volume. That will drive a lot of the costs and everything else. So whereas while there may be a very good technology for certain applications and trying to drive down the cost, the business case may not be there. Okay? You know, with that said, I think I may have a question for Evan here too, because I know we've dealt with, you know, NASA has dealt with the DoD and, you know, quite a bit and everything, and it's the power community is very close-knit. But from my point of view, DOE is the big dog in the field here too. It's a very large organization, does a lot of research and everything else too. I'm just curious about your perception out there from PNNL in terms of the coordination with maybe some of the other organizations and everything else. And I'm always interested. I know we've dealt with the National Renewable Energy Lab out there quite a bit and everything, but in terms of our interactions with some of the other DOE labs, it hasn't been quite as much too, and I'd just be interested in your perspectives on any of that.
So from the power perspective, we do a pretty decent job of collaboration across battery systems, lithium sulfur batteries. There's a very gigantic really community there, and I think that works pretty well. I think from a fuel cell perspective, we've only really worked closely with the Navy, and that's specifically NAVC, and also with TARDEC, and that's the Tank Automotive Command, because that was a specific mission set that we were approaching. So we kind of organized around a mission set. For TARDEC, it was auxiliary power units for trucks, Abrams tank specifically, and then the Navy is moving pretty strongly into looking really at you getting a UUV fleet in place. They have a large procurement that's being planned. So with that, the power systems on the UV are one of the critical enablers for those kinds of things. So that's really, the collaboration that I have seen has typically been groups of 2 to 3 in general. It's not been like you have a giant community of interest pursuing a common objective. It's always been, what I have seen is 2 to 3. And I guess I'd call it a constellation. Sometimes you'll have a constellation. You'll have a couple of plants that are working together, all part of this big community, but it's really, really difficult, in my experience, to get, say, like 5 or 10 organizations working together, common objective. That's really hard. I don't know if anyone else has any experience on that, but my experience with other orgs, whether it be other national labs, other agencies, other private companies, if you keep it to 2 to 3 with a common strict objective, that I've had more success with those. Then we can keep this information flowing, but the information flowing is meant to make connections, so you can help to form these 2 to 3 party interactions. That's, in general, how you might want to look at those groups. Those groups in and themselves can't accomplish an objective, but those groups can put together a community of interest where you'll have 2 to 3 realize that they have a common interest and a common objective, and then those can go forward. That's how I sort of see it.
Any other comments on that too? Phil, I'd be interested in your perspective from the DoD community too, because the Navy has their own focus. A lot of that has deals with underwater, some underwater applications too. But you would think there would be more coordination maybe between the different services with regard to the power stuff. I don't know if you have any comments on that to the degree, or is there more focus in one area versus another? Or?
Right. So before we started working in terrestrial systems, I sort of heard this, that each service is sort of their own stovepipe and they develop their own technology. But my experience has been the opposite, is that we've always had a close relationship with the Air Force Research Lab on space technology, and they are also interested in, for example, this UAV application. The Army has, when they found out the sort of work that we were doing with the Marine Corps, the Army Research Lab was very interested in that, and we're right now have a joint field demonstration with sort of Army supplied equipment with Marine Corps subjects, if you will, testing out new technology. So we've had a pretty good synergy on the PV side between the services.
Okay. And if I could add maybe a point onto that too, is that I understand what you're saying about the stovepiping and everything, and through my history there, and I've noticed that a little bit with IAPG, is that I would have comments from the different agencies. You'll be the first one to acknowledge that, Navy, Air Force, Army, those are big organizations. They don't always talk together as well as you would hope them to be too. And I agree with you in terms of the space area. There was always a lot of coordination between the different agencies and everything else. But I remember a number of years ago, I would be talking to people like with the Air Force, and they were asking, about advice on photovoltaic technology and other power systems and everything. And I don't think they realized that they had their own experts within the Air Force or had close contact with them. Now, the one thing I have noticed over a number of years, given the push on renewable energy and energy technology and everything, that has drastically changed. I've noticed that particularly within DoD, there is a lot of coordination at the very high levels. It seems like it's been dictated on from the the highest levels of management on down, that it will be coordinated, and people I believe have been added responsibilities to make sure that stuff gets coordinated, not only within the services, but between the services as well.
Just to back up a little bit, the question from the audience about gallium arsenide to commercial applications. There are technologies where the gallium arsenide makes sense, and that's with these concentrator systems, where essentially the way you reduce the cost of the solar cell is you make a much smaller cell, right? You have a cheap lens that focuses it onto a tiny cell, and then they can be cost competitive. And silicon is a moving target, right? Every time you get them in your sights and you think you're going to beat them on price, then they lower the price. But there are still opportunities out there for gallium arsenide to make it in. I wouldn't say so much your rooftop in your backyard, because these concentrator systems have a fair amount of infrastructure with them, but at the utility scale, which could lead to production scale, economies of scale gains, would make these systems that much more competitive.
Please.
Kind of a similar question. So why are the multi-junction cells so expensive to make? I mean, if you're getting twice the efficiency, you could make them at twice the cost and still come out pretty good. But I saw $50 a watt up there, and that's pretty darn high. I mean, that we're talking an order of magnitude over the cost of cells that you just get at Home Depot or whatnot for the silicon.
Right.
So why are they so hard to make? And it can't be just volume. We're talking really big numbers here. So can somebody answer that?
Well, first part of it, Ralph, a lot of it is, part of it is the sort of the bottlenecks that I spoke about earlier about this epitaxial growth that takes a long time. It works over a small area. But don't discount economies of scale, right? Because the rule of thumb I heard about price reduction was that every doubling in volume, you get a 20% reduction in cost. And we're looking at hundreds of kilowatts versus whatever, tens or hundreds of gigawatts. So there still is a lot of economies of scale to be gained.
Also getting back to the silicon market and how it has been dominated by the Chinese supply, cost and price may not necessarily be related in terms of the silicon market, because there was a great increase in capacity undertaken in anticipation, and that overshot the market by quite a bit. And it's, again, economies of scale, but also an issue of oversupply versus demand.
Yeah, from a cell manufacturing perspective, a couple of things you can say. One of the technology is very capital intensive, so the basic technologies you need to spend a lot of money to be able to initiate the process. So that is one thing. Number two, as I said, the volume. There are examples where gallium arsenide has dominated, and a very good example is your cell phones. Most of the power amplifiers in your cell phones are all gallium arsenide. So when you see that there is a niche application, there is volume, the cost of the cell phone is minimal now. So it's all question of what is the killer application that can make the performance the key factor.
And that killer application is space, right? As soon as gallium arsenide came on the market, it instantly replaced silicon solar cells because they're an order of magnitude more radiation resistant than silicon. So you're always looking for that unfair advantage.
Okay. If anybody else has any more questions from the audience, but please go ahead.
Again, perhaps an inappropriate question for this session, but SBIR was mentioned several times by various people here. What funding mechanism should universities be looking into to participate in research in these areas? I know NASA has the NRAs. Does DOD and DOE have similar sort of mechanisms?
I can handle that question. There's a parallel program to SBIRs called STTRs that are university oriented. So if you use Google and look up STTR, you'll find that there is a separate set of funding that's associated with universities in cooperation with small businesses to do innovation research.
I think from a DOE perspective, there's a lot of university-only funding vehicles. There's a lot of research programs that are specifically directed towards universities.
How are they announced?
Oh, man, DOE is a very big organization. DOE is a very big organization as much as DOD. I think you'd want to really just start at the DOE webpage and you start diving into it and you look at university-affiliated research. I think you'll find a lot of different programs in there because you'll also, there's dozens of BAs that come out of DOE every month, and many of them, they'll describe specifically that they're directed towards universities.
There are two web tools that you'll find useful if you're looking for funding. One is FedBizOps, and the other is the NAIS, which is the NASA version of FedBizOps, which there is some overlap. But you can use both of those tools to figure out when the announcements come out, what is the requirements, where does the money come from, how do you get
FedBiz has everything from planes and ships to university-affiliated research. So that's the federal government procurement site.
Yeah, it's everything. So there's a lot of data there, obviously.
And as a side note too, there are, I don't know where it is, how it is throughout the country, but here in Northeast Ohio, there's an organization called Nortec that does a lot of work like that too. And I receive an email from them on a regular basis that said, here's the latest Air Force solicitations, Navy solicitations, NASA solicitations. So I would assume the same thing exists in various areas throughout the country. So, but just as a general note on SBIRs and STTRs, at least from my perspective, being a technologist in the power area, we have really utilized that program to the hilt. As we had talked among ourselves here too, and Ted particularly talking about the decline in basic R&D and everything else too, with the fluctuating budgets and everything else. The one thing that has been very steady with that, even though agree that the time frames may have shifted a little bit and things change based on budgets or sequestration, the SBIRs, from my perspective, have been a godsend with regard to developing advanced technology. It does not always pan out, but a lot of the technologies we've worked on right now have had their start in SBIRs. As Randy mentioned, a lot of the SCP programs with some of these 100 kilowatt stuff, we have fully leveraged some of the advanced array technology through SBIR programs, and there has been a lot of success in that program itself. So that's been very good then. So, any other questions? Please, go ahead.
Being a solid propellants guy, I don't have a lot of background in terms of the advanced energy. You were talking about a trip to a mission to Venus. You would have to probably use a flywheel type system to overcome the temperature effects. Do you envision a situation where we have maybe a standard launch vehicle that can have interchangeable energy systems? And if we did something like that, is there any work being done in terms of making the power management easily interchangeable with the different types of power storage units and things?
Well, I would say NASA is looking at modular power, not so much on launch vehicles as in spacecraft, manned spacecraft and unmanned, but looking at some standard modular components that can be interchangeable. And even playing with the intelligent grid aspect so that the grid can recognize those changed out parts and accommodate those. So we are looking at that. That's a very good question. We have a program underway right now. A lot of it is in Cleveland, but it's throughout the agency to work on those modular components.
Randy, if you don't mind, I'm going to pick on you on this one here too. So, Randy had mentioned our previous reorganization and everything else, and I'd just be curious to put Randy on a spot here with regard to, Randy's been with NASA his entire career, a very long time and everything, but the area of power is relatively new to you. You haven't had a lot of experience in that, and I'd just be curious. A lot of us up here have been working the same programs for a long time. We get a little stale too. I'd just be curious, with regard to this whole topic here about, power, coordination. You're getting a lot of this stuff fairly fresh right now, and I'd be curious about your perspective on that in terms of, are we coordinating enough? Are we focused enough within either the NASA programs or some of the others. So,
Yeah, I'd look at that two different ways from what I've seen. The IAPG that you talked about is a tremendous organization for coordinating across government agencies. As I began to get involved in that, I was surprised at how well that works and how much power-related communication is taking place. But I was more surprised to find out that that organization's been in place for 50 years, I believe. This is not a new thing. This has been going on across the government for a long time. And most of these agencies have been members throughout that whole time. So from that standpoint, across government, I have been impressed with what's going on. I think part of the problem, though, also has existed within agencies. NASA has 10 different centers that can be competitive. DOE has multiple laboratories that I'm sure can be competitive. But so the coordinating across entities within an agency is a challenge. And as Mike's fully aware, at NASA, we've spent the last year and a half developing somewhat of a prototype partnership within NASA. We've been coordinating across 2 centers. We took the Glenn Research Center, which isn't just research. We do research, it's a hybrid center. We do research through flight hardware and operations, and have been working on a partnership with the Johnson Space Center in Texas, which we do a range of things, a lot of it robotic. They do almost exclusively human exploration. And we've worked closely in that year and a half establishing a true partnership between centers, trying to get away from the competitive and more to looking at how what they do in power enhances what we do and vice versa. And it has been very effective to date. All of our people know all of their people now, and did to some extent before, but now it's very much on a more of a camaraderie type basis, and looking for the driver for us is probably the same driver that works across government, and that is as resources are drying up, as there's less and less programmatic dollars, you can't afford the luxury of duplication and competition. So we really are looking for ways that the 2 centers can work together on a project as opposed to repeating and fighting over a project. So it has been effective. We built a whole taxonomy of power and laid out step by step where the center of gravity is between the 2 centers, and worked that to reach complete agreement, basically, on every step of it. So I'm seeing that improve. We could always do better. That's one prototype that's doing very well. We've got 10 centers that all have to work things like this. But that's what I've seen so far in a nutshell. I think the coordination across agencies is better than I thought it was coming in, and coordination within the agency maybe hasn't been quite as good as we'd like, but we're working it. That's how I'd see it.
Okay. Another question here too. I'm looking at Ted and Rao here too. As our industry counterparts here, I'd just be curious. I know we touched on this a little bit, but I'd be curious about your perspective in terms of you've had a chance to work with different agencies. Maybe not everyone here, but with different agencies, and you've seen differences between the way DOE, NASA, DOD, how they'll work and everything. Do you have any comments, suggestions, observations, related to that we may find useful here? Either one of you two.
I'll take a shot.
Well, I think we find that there seems to be kind of a small last mile gap in the development process, and there is a lot of technology development taken to one stage, and after that there seems to be a gap between actual implementation, and either it is a field trial, or in one case here where we have NRL has done a very effective way where they actually shown the product being utilized in the field. But in a lot of other cases, for example, in space applications, it's very, very tough for us to actually cross that last hurdle, where to qualify for the technology. And that kind of funding seems to be, there's no clear path for that. There are a lot of different ways that one can approach it, but there is no clear path for a newcomer. So how do you cross that last?
The well-known Valley of Death.
Valley of Death.
We've known, everybody has talked about that for a very long time, and from my perspective too, is that kind of like you have certain organizations that are very focused on the R&D, so that lower third of the TRL level is fine. You have programs that have funding that that look at the higher TRLs and qualifying the stuff too, but it seems like all those organizations are pointing at each other and looking for the funding and trying to get over that mid-level area. So.
Yeah. I think coordination between the research centers is quite good, even across agencies and between DOD and NASA, Department of Energy. Sometimes what I find lacking is the coordination between the research agencies and the mission users as far as what technologies do they really need and what is the mission going to be in 10 years. And part of that is coordination between the agencies and Congress and whoever ultimately decides what NASA's mission is going to be, what the next DOD mission is going to be from the very top level perspective. Right. So, and some of that has got, that's always in flux, and I think some of your challenge is figuring out how do you shoot ahead of the hare and figure out what technologies that can I develop that'll get me to Mars, but also if Mars falls out of favor, will get me to an asteroid or to get me to L5 or whatever the next administration is going to dream up is going to be the new mission for NASA. So that's a challenge that you have that I don't know how to solve. But getting more input from the user community, both from the flight centers in the case of NASA, from the operations center in the case of DOD, and even from the commercial communities that are tending to drive a lot more of the technology, is something that would be more valuable.
Right, and it's similar to that as well too. And we've seen it before with the NASA, and we all shake our heads as technologists, is that we look at missions, they decide on a mission or something like that too, and they're over there, they look at everything, they start letting contracts out and everything without mission requirements. And they make decisions based on the fact that, okay, this is what we think we need, but you don't have their mission requirements set down yet to the point where, oh, I guess that won't work, or decisions have been made or said, we don't need that sort of technology. There's been in many instances where they said, we don't need to develop any advanced power technology. We'll just take and buy it off the shelf commercially and everything. Oh, and by the way, we needed to do this, this, and this, which if you talk to the technologists, you'd realize that technology does not exist. And so there are disconnects in many ways with that. Okay, with that, we've been at it for just over an hour and a half there too. If we have any, last-minute questions from the audience, and if anybody of the panel members want to make some last comments and everything else, I'd appreciate it, and then we can kind of wrap up here. Please.
Okay, yeah, great. I just had a quick question sort of on the technology side of things in terms of advanced energy concepts and working amongst the department, the government agencies. Is there any work going on in directed energy in terms of transferring energy from one location to another? I know there's like directed energy weapons that I've heard about, but in terms of that logistics, management of trying to get energy into the field or a certain location, is there any work going on in that area that you're aware of?
I know there's some wireless power research, but that's more like, rather than covering the soldier with a bunch of cables where he's running power to all his batteries and so forth, they have some sort of wireless transmission grid. That's sort of the small scale application. There have been a number of, I would say, proposals for power beaming, right? Either laser power beaming or RF power beaming, but nothing has gained enough traction to where they're developing a demonstrating system.
And with regard to some of the power beaming stuff, a lot of people have looked at it at very large scales, and the problem is that to have it make sense, economy of scale and everything, you have to have a whole system in place, and the upfront costs for that have made it prohibitive. One area I keep thinking about where it makes a lot of sense and might be the first implementation of that is something, similar like you have for NASA, potential NASA missions, remote sensors or something like that, where if you're, just like pulse lasers or something like that, if you're using that as a comm unit, there's no reason why you can't take and incorporate energy conversion with that. This, combine comm with propulsion. That's one area we've looked at a number of times. It gets to be difficult from a system point of view, but combining, power with comm, power with propulsion and everything, there's a lot of concepts with that, but as far as I know, they're just concepts at this point and everything, and the real mission need at that point I don't think has been defined yet. But definitely there are people looking at things like that. So.
Hello, I'm John Thomas. Professionally, I'm a systems engineer, and so I was very intrigued, Ted, by your comment about some insight into the higher system requirement. As a systems engineer, I'm used to not necessarily being too welcome down in the R&D organizations. But I've been an advocate that we're the very elements that in one form or another should be able to give you broader insight of how to direct the technology development of the components. Since we have the insight of how we flowed the things down to the subsystems and et cetera. So would you share what you feel like you could do that would be more productive in the technology development of the components if you only had a little bit more of that information?
That's a great question, and I think it was echoed by what Mike just said, that lots of times we have the mission name identified, but we don't have the mission requirements, which is the exact problem you're talking about. That is the system engineering problem, is you don't have that top level spec that then takes you down to the next level, the system level, the subsystem level, eventually the component level, which drives a lot of the research and development dollars. So, if you go back in history, there have been times when it's been done correctly. On the original mission to Mars, someone who was older than me, who was around when the spec was first released, said that the spec that Martin Marietta got, the requirement was build a spacecraft that can land safely on Mars. That was the top level spec. So they defined exactly what they were after, and then it was up to the contractor to figure out how do I flow down that spec, which is ultimately what systems engineering is all about. It's taking requirements, flowing them down, dividing it up, and figuring out how do you meet those requirements and verify them. I think in the community, and this goes for the academic community as well as the engineering community in government and in industry, we lack system engineering training and skills to really do what you're pointing out. And that's, I don't know if I've answered your question, but
no,
you've identified the problem, and the answer is a lot harder to come by.
what I was trying to ask, as a technology advancing entity, your company is all about that, and it's at a component level. I felt like you had mentioned if you only had insight
Yes.
into the higher level, what as the R&D element of that component, what could you do better? That's the question I've got that I'm trying to get some insight into. So instead of simply being told, you got to go make it thinner, your example was, don't tell me just simply that I need to advance technology to make something thinner. I would like to have the broader context of that requirement so that I could actually perform some trade space as well. And I'm wondering how you would take advantage of that to be a better technology component developer.
Oh, I think, yes. And I think you're answering your question in a way. You create the traits. Once you understand the top level requirements, I mean, you're ultimately, everything comes down to cost. Can we afford to do the mission or not? How do we afford to do the mission? If it's thin cells, it may be because it's lighter, because the launch cost is $100,000 a kilogram. If it's higher efficiency, maybe it's because the arrays need to be smaller, because the spacecraft lifetime is limited by how long you can do attitude control propulsion. And that translates into dollars, and in the commercial world into revenue dollars, because your spacecraft lifetime is related to revenue dollars. So ultimately, the research and development is about achieving the most cost-effective solution to a problem. And understanding what the problem is at the top level could allow me, as a research director, to go and do that trade-off to figure out, do I need the cell to be, 1 mil thick or half a mil thick, or is 5 mils thick okay? And what is the trade-off between mass and volume and deployed area, and how do I come up with that best solution at the system level? And then figure out, okay, in order to do that, I have to apply these research directives in order to develop that technology. I know it's still it's a very general answer to your question, but that is what I would like to see.
And Randy, I don't know if you want to make a comment on that, but under the reorganization, we did set up a separate system engineering organization, put them off to the side to, at least note that system engineering is important. So.
Right, and by setting it separate, we have 4 core competencies, technical competencies, and then we set up a systems engineering division that cuts across. So it's a shared competency across, but it highlights the criticality of systems engineering, but it also, to me, shows how it's an integrating function across the competencies. So, I mean, it has yet to play out on how effective it's going to become. This has just come into place. But it seems like the structure's right now to make maximum use of that capability. All the systems engineers aren't in the systems engineering division. The competencies have them as well at more focused systems within power, for instance. But I view, and I think a lot of us do, that the systems engineering organization is almost like playing the role of an engineering society across the organization, of assuring that the systems engineers within the competencies have the proper background and training, not just high-level systems engineers across the full system. The structure's in place, at least.
Okay, with that, if we don't have any more questions from the audience, do any of our panel members have any questions or last-minute comments or anything? Okay, with that, I
just want to thank you for arranging the panel and for such an interesting topic. Thank you, Mike. And
I appreciate that. Okay. I'd also like to thank all our panelists here, too, in the audience. All right. Appreciate it. Thank you very much.